Inshallah. Okay, so as you know, we have started the chapter 2. So we continue at chapter 2. I think we have completed this one, right? Transfer function. We have completed the transfer function, and is it visible to you, the slide?
Yes, sir. Yes, sir. Yes.
Okay. So let's repeat something, because in the meantime we had a gap, we had a vacation. So let's review something. At least this chapter. Okay, module 2, modeling in the frequency domain. Inshallah, we will finish this chapter within one more class. I'll take one more class to complete this one. Okay, then we'll go to the chapter 3. So our target is that before the midterm, we'll complete the chapter 4. We'll complete chapter 4 for the midterm, up to chapter 4. Okay. So for the midterm, you 1, 2, 3, and 4. These 4 for the midterm, and for the final 5, 6, 7, 8, 10. Okay, these are for the final. That is why, since final has many chapters, that is why I am trying to complete chapter 4 before the midterm. Okay, it will be easy, not very difficult, you know.
Okay, sir.
And put the questions like that way. Okay.
Okay, sir.
So we have started this one, modeling in the frequency domain. You know, there are 2 domains. Do you know that 2 types of domain are there? One is frequency, one is time domain. So if I review something, I think you should know that time domain is very known to us, right? Say this is x-axis. In the x-axis, you are getting the t, and this is the y-axis. In the y-axis, you are getting, say, amplitude or magnitude. Okay. Here, the amplitude, the amplitude. Let's draw a signal. This is what? This is a signal. What we are seeing. It is moving on the time domain. But if you look at the frequency domain, then what you will see? The frequency domain, you will see just pulse, this kind of pulse, right? And here the frequency. Okay, I think you already know that. In the communication engineering, I have shown those things, right? Time domain and frequency domain. This is the frequency domain, and you had a problems. So that is the frequency domain. As a time, but in the time domain, you see the total wave.
Okay, sir.
I think something like that. So something like that. I cannot draw 3D. Whatever. So in the control system, so you know, in the control system, what is the basic thing? You will give an input and you will get output. In between, there is a system. you can divide the system into many parts. Okay. So that is the block diagram of the system. So you're giving input RT and you are getting output CT system and subsystem. You can divide the system into several subsystems. Okay, several subsystems. You can divide the system into several subsystems. Maybe 1, 2, 3, 4, 5 multiple blocks. You can divide it into multiple blocks. Okay. So remember that input is RT, output is CT, and you know C of S divided by R of S. That is the transfer function. That is transfer function. A for transfer function, we can represent this thing as the GS. Transfer function, we can represent the transfer function as the GS or TS. If it is the closed loop, then it will be TS. Okay. So here the RT, the input is known as the reference input, and the output CT, which is known as the controlled variable. Okay. CT is the controlled variable. Okay. And we have to remember this table, Laplace transform table, delta T. In FTFT is the time domain, F is in the frequency domain, or the S domain. That is the Laplace transform. We have to write this thing like this way. I think your in the mathematics course you have seen these things, right? Anish sir have shown you those things, right? Laplace transform. That is the Laplace, and in the signal system also. That is the Laplace transform representation LT. Okay, L of T, and it is actually S domain. Laplace transform is actually the S domain, frequency domain, and that is the formula. And if you do the inverse Laplace transform, then it will be like this. Here, the S is sigma plus j omega. So how to represent the S domain? See here, I'm writing. That is the S domain. Here, j omega. Here the negative j omega. Here is the sigma. Here is the negative sigma. Okay. So that is the S domain. That is S domain. In the S domain, we have to show this thing like this way. Okay. So sigma, positive sigma, negative sigma. Sigma is the real value. Here, sigma is the real. That is the real value. And j omega is the imaginary value. J omega is the imaginary value. Sigma is the real one. Okay. This space is known as the S domain. Okay. I think frequency domain. This domain is the frequency domain. Okay, in the meantime, we have seen the problem, which is the example 2.1. We have seen the problem 2.1. So what they say, I think you can skip this one. And partial fraction expansion, we have shown to you how to reduce this one. Partial fraction is important because okay. Another example, transfer function, it is the ratio of the left. What is the transfer function? It is the, you have to remember this one. It is the ratio of Laplace transform of the output to the Laplace transform of the input of the system. So Js is equal to Cs by Rs. Remember this one. So here is the problem is given. Find the transfer function represented by dct, dct by dt plus 2ct is equal to RT. So here, one thing you have to remember that d by dt, that is S. And if you write that d square by dt square, that is base square. And if you write dq by dq, that is the square. That means if you take the Laplace transform of this one, then you will get the S. That is what? Laplace transform of d by dt. Okay. Then you will get S. And if you take the inverse Laplace transform, then you will get this. Remember this thing. Okay. So it is a simple one. Since transfer function is important, so let me show you again. First of all, what they did. First of all, take the Laplace transform of the both sides. Then SCS plus 2CS is equal to RS. Right. Then what you will do? Do one thing. Take the CS common. Take the CS common. Then what you can write is plus 2 is equal to RS. So according to formula, CS by RS is equal to GS. So put it here, C of S divided by R of S. Right. Then what is it? 1 over S plus 1 over S plus. Okay. So you get the 1 over S plus. So GS is equal to CS by RS is equal to 1 over S plus. So that is your transfer function. So you can write like this. So here you put the RS. Here you put the CS. In the meat, you put 1 over. Okay, so that is the way you can represent the problem accordingly. That is the technique we will follow. Okay, so another example is given here. System response from the transfer function. So also you can do the vice versa. So if the RT is the UT, that means the input is the unit step function, then how you can write? So instead of RT, you have to write the 1 over S. So RS into GS. So 1 over S, S plus 2. So here they have used the partial fraction. So partial fractions, for the partial fraction, you know what you have to write. Write 1 over S into S plus 2 is equal to, say, A by S plus B by S plus 2 for the partial fraction. Then you can do this multiply this A into S plus 2 plus Bs. That is your new equation. Now what you'll do, then put the S is equal to, say, S is equal to 0. If you put the S is equal to 0, then it will be 1 is equal to twice. That means A is equal to 1 by 2. A is equal to 1 over 2. And if you put the S is equal to minus 2, then it would be 0 and minus 2. Then it would be B is equal to minus half. B is equal to minus half. Okay. So we can represent this equation like this: 1 by S into S plus 2. Instead of this equation, we can write this one. Half divided by S minus half divided by S plus 2. And if you take the inverse Laplace transform of this one, then it will be half of S is equal to 1 minus half into, since it is S plus 2, it will be over minus 2p. Okay. Because we are taking the inverse Laplace transform. So to understand this, you have to go to the back. You have the table. See, UT. Instead of UT, you can write the 1 by S. Or if you take this inverse Laplace transform, then it will be O. Okay. This is also one. So that is the way you can do the Laplace transform. Important one. It is we are starting the new part here. Electrical network transfer function. Electrical network transfer function. Voltage, current, voltage, charge, and impedance relationships are for capacitors, resistors, and inductors. Here we are seeing some relationships like voltage, current, voltage, charge, and impedance relationships for capacitors, resistors, and inductors. Okay. These are the relationships. So if you look at the table, then you'll see this. For the capacitor, resistor, and inductor. See, first of all, what they have shown, the voltage current relationship. You see for the capacitor, what is the relation, and the resistor, what is the relation, and for the inductor, what is the relation. For the capacitor, it is V of T, voltage. So we have to find out the relation between the voltage and current in terms of capacitor. See here, Vt is equal to 1 over C, integration of 0 to 1, I tau d tau. Okay. The current. Tau is equal to actually RC. Okay. And for the resistor, Vt is equal to Ri. And for the inductor, LD by dt of I. And there is the current voltage relationship, there is the resistor relationship. Impedance and admittance. Impedance Vs by Is and this Ys is equal to Is. Okay, you know the impedance Zs V by I. So impedance is what? Z. Z is equal to V by right. V by I. Why the small letter? Because it is AC. For the DC, that could be resistance and it could be V by I. You know that for the DC current, there is only only resistive part is there. For the AC, inductive and capacitive part will arrive, right? For the DC, only resistive part will be there. But if you consider the AC, then the inductive and capacitive portion will come. Since why inductive and capacitive portion come? Because AC it is continuous, right? But DC is straight line. So capacitance and inductance, those are the charge storage component. So how the charge is stored due to AC? Because back and forth, right? Okay, those are the things from the circuit courses. So I'm not interested to show you again those things. Okay, so remember these things for the capacitor, resistor, and inductor. You will regard this one. For the impedance, Vs by Is, and admittance is what? Admittance is 1 over Z, right? Admittance is 1 over Z. Admittance is 1 over Z. Okay. Admittance is 1 over Z. That is why Ys is equal to Is by Vs. Okay, let's move on the problems. I am more interested to show you the problems. Example 2.6. Take a look. look at the problem here. What they have said. This is what? This is a RLC network, right? That is a RLC network. They have said that find the transfer function relation relating the capacitor voltage. It is a capacitor voltage is the VCS. Input voltage VS in figure 2.3. So this figure I have shown you. So we have to do something, but okay, there to stay. Okay, so first of all, what we have to look at the figure very carefully. This is what? This is a source. What the source is here. That is the capacitor L, resistor R, and that is the that is the inductor L, resistor R, and the capacitor C. Okay, so it is a RLC network. So we have to find out VCT divided by VT. VCT by VT. Okay. Because find the transfer function relating the capacitor VCS to the input. So VCS by VS, we have to find this out. But here it is given as the VCT, and that is given as the VT. Okay. So what do we have to do? So first of all, let's take the summation. Apply the ohms. Apply the KVL. Okay. First of voltage KVL. Loop. You have to apply the loop. So according to the formula, V of T will be equal to L inductor, resistor, capacitor. So we can write L DIT by dt RIT plus 1 by C I tau dt. That is what. Now go backward. Previous slide. See, voltage current relationship. We have shown the voltage current relationship here. Voltage of the capacitor can be written like this. Voltage of the resistor can be written like this. Inductor like this. These formulas have been applied here. So for the inductor, we can write like this. For the resistor, we can write like this. For the capacitor, we can write like this. Okay, that is a V2. Is equal to V2. Now changing the variables from current to charge using IT. As you know, IT current is equal to what? Change of rate of charge. That is the IT. Okay. So instead of IT, what we can write? We can write the dQt by dt, right? Instead of IT, we can write dQt by dt. So changing variables from current to charge using IT is equal to dQt by dt. So applying this, we can get this. Here, do you understand how we get this one? I think let me clear to you.
Yes, sir.
Just instead of IT, move this one. dq by dt, then you will get this one. Here, instead of I tau, if you put this one, then D28 will be cancelled out, and only Qt will be there. Because if you do the integration, then 1 over C will be there. Okay, so that is the reduced form, new equation. Now, instead of Qt, you can write the CVC. Now, for this one, you have to look at the previous chapter. Previous table. Instead of Qt, just see this one. Table 2.3 Qt is equal to CVCT. Qt is equal to CVCT. Here, look at here. What they did, see, if you look this equation, see, Vt is equal to 1 over C into Qt. So Qt would be what? Qt is equal to Vt into C. But if you CVT, actually CVT, they write like this: C of instead of Qt, write like this. So it is here, the VCT is here, so we can write the VCT. Okay, put this value, then you will get this one. Now, what you will do? Taking the Laplace transform. Now, let me show you how to take this one. Okay, now the important part. Take a look here very carefully. If you take the Laplace transform of this equation, then what you will get? D square by dt square, right? So you can get LC d square between dt square by that is the s square. DCT, that means the VCS plus RC. DDT, that means the S. DCT, that means the VCS plus VCS is equal to VS. Now our target is what? VCS by VS. Now it is easy. Now see here. Now first of all, I'll take the VCS common. Take the VCS common. Then what you can write? LCS is square. LCS square plus RCS plus RCS plus 1 equal to VS. Now again, VCS by VS. VCS by VS. 1 over LCS square plus RCS plus 1. Now do one thing. Divide this thing by LC. So if you write VCS by VS, that is our transfer function, which is equal to 1 over LC by S square. So plus, if you put the 1 over multiply it by LC, then R by L. R by L is plus 1 over L. Okay, that is your transfer function. That is your transfer function. Then you get the final result. Okay. So what so that is your final equation. So finally, you can represent it by the block diagram. Input is VS, output is VCS. Block diagram. Inside the block diagram, what you have seen? You have seen the 1 by LC divided by S square plus R by L S plus 1 over LC. So they take the VCS common. After applying the Laplace transform, they take the VCS common. Then they find out the VCS by VS, which is the 1 over LC divided by S square plus R by L S plus 1 over LC. So that is the equation. That is the final transfer function equation of the problem. Okay, so we have to look at this one. Okay, now they have developed two things. Let us now develop a technique for simplifying the solution for future problems. First, take the Laplace transform of the equations in the Bundescard column, table 2.3, as well as zero initial conditions. For the capacitor, it would be Vs is equal to 1 over Cs into Is. For the resistor, it would be Vs equal to 1 over Vs equal to R into Is. For the inductor, it is Vs equal to Ls into Is, and transfer function will be Vs by S into Js. Okay. So for the resistor, it would be R into Is. For the inductor, Ls into Is, and for the capacitor, 1 by Cs into Is. So if you do remember these things, then you can easily complete the problems. Okay, so you have to remember these things. This shortcut, these shortcut format you have to remember. Otherwise, you cannot proceed very carefully. Okay, so for if you have the capacitor, so you can instead of the capacitor voltage, you can write like this one, 1 over Cs into Is, and for the resistor you have to write Vs is into Ris, and for the inductor you have to write Vs into Ls into Is. And and you know what is the Zs? Z is the Z is a impedance. So impedance. So instead of impedance, you have to write Vs by Is. Instead of impedance, you have to write Vs into Is. Vs by Is equal to Zs. So here is another example, shortcut form. So without using this Laplace transform. Mesh equation. So they use the mesh equation. Yeah. So for the mesh equation, what do we have to do? we have to follow few things like this. Look at the figure here. Let me draw. We have the voltage source. We have the inductor. We have the resistor, and we have the capacitor. That is our circuit. And here the current that is the IS. That is the whole ABS. That is the ECS. Okay. So here what you can write? You can write the VS. This is these components. Summation of these components multiplied by I. So these components, instead of this, you can write as RS and 1 over CS. Just summation. Summation here. And now IS by VS, this one. But the voltage across the capacitor VCS is the product of the current and the impedance of the capacitor. So impedance of the capacitor is the product of the current. So IS into 1 over CS. Now put this value instead of IS. So instead of IS, we can write. So let's say this instead of IS, let's put this one. CS will VCS into CS, right? By VS is equal to 1 LS plus R plus 1 over CS. Now, what you have to do? Now, just divide the both side by CS. So if you transfer this only, that will be 1 over 6. 1 over 6. Then if you can do the calculation, then you get the simplified equation. Like this. Okay. So instead of IS, we have to add like this. This is in this. Now do the equation. And then now if you write the BC by B 1 by CS equal 1 over LS plus R plus 1 over CS. Okay. Now do the calculation here. Multiply it by CS, this part, upper. And after the calculation, multiply it by CS1. So if you multiply it by CS, then LCS square, LC this square plus if you RCS plus 1. Then do one thing, 1 over LC this square R divided by L inverse plus 100. So similar equation. Okay, so you do understand this one, like the previous problem. Okay, I think you do understand the problem here, right?
Yes, sir.
Now look at the mesh equation. How to do the mesh? Complex circuits via mesh analysis. To solve the complex electrical networks, those with multiple loops and nodes, using mesh analysis, you can perform the following. So you are familiar with the mesh equation, right? So like this, let me draw a circuit. Let's say I'm considering a circuit here. Simple one, not complicated. Let's say this is a I1. Side. Okay. So this is a circuit. Okay, two loop. So you can apply the two loop. Loop one, that is the loop one, that is the loop two. Same. So here we use the mesh analysis. In this kind of circuits, we have to use the mesh analysis. Okay. This kind of circuit can be used for the mesh analysis. Some of your friends still joining. Okay, so what is the process? First of all, replace passive element values with their impedances. So these elements values will be replaced by their impedances. They replace all sources and time values with their Laplace transform. So these sources will be converted to the Laplace transform and the time variable. And assume a transform current and current direction in each mesh. And direction we have to consider the time direction here. And KVL, apply the KVL here. And solve the simultaneous equations for now. And form the transfer function. These are the complex circuits via mesh analysis. So these are the complex circuits. Okay, for the mesh analysis, we need these complex circuits. Okay. So to solve the complex circuits, we need to use the mesh analysis. Okay. So let's look what I have told you. This kind of circuit. Okay, so that is say I want to listen, that is I22, here the L, here is the R. There is the capacitor, inductor. So replace these things. Say Vt, transfer it to the Laplace transform. Instead of Vt, we have to write the Vs. Instead of I12, we will write the I1s. Instead of I2t, we will write the I2s. And here the capacitance, here is the capacitance impedance. So 1 by Cs, R2, R1. And these are the node, LS, VCS. So inductive voltage lies here in this node. And capacitive voltage, VCS. Inductive voltage, VLS. So transfer function of this one, this circuit. Okay. The problem, mesh problem, we'll see in the next class. Today we have almost finished.
Yes, sir. Yeah.
Lots of things we have discussed today. So So before the ending the class, I have to take your attendance.
Okay, sir.
Some time. So far, how many classes has gone?
6, sir.
1, 2, 3, 4. This is 5th class, right?
Yes.
Okay, let me give me some time. Today is the 20th of May. Okay, so roll number 2 is here. 6 is here. 10 is here. 12, 14.
Yes, sir.
18. Okay, let me check. Roll number 2.
Answer, sir. Answer.
Sir, roll 10.
Yes, sir. Yes, sir.
Roll 6.
Stay, sir. Mountain. Yeah.
Roll 10. Smile.
Yes, sir. Yes, sir. That's mine.
Roll 12.
Yes, sir. Alright. Yeah.
Roll 12. Roll 14. And
40. Yes, sir.
Also roll one, sir. Sir, roll one, sir. She disconnected Diba now.
Diva, where is
Yeah, she's disconnected. She's telling me in Messenger.
Okay, okay. So roll 1 is here.
Yeah.
9, sir. 9.
So complete. Right? Okay.
Yeah.
So for the lab, I have a plan that I'll give you the YouTube link video. YouTube video. Today I'll record a video, a YouTube video, then I will upload for your lab. Okay.
Okay, sir.
I think
Okay.
that will be more easier for you.
Okay, sir.
So you have downloaded